Hello friends, welcome to the YouTube channel Spectrum Science. In today's video, we will discuss about inductor. There are a variety of inductors available in the market depending upon the shape and size of the inductor and the core used. The air core and the iron core inductors are used for low frequency applications, and for high frequency applications we use ferrite core, as normal core cannot respond at high frequency applications. Now let us discuss applications of inductors. This inductor along with capacitor forms an oscillating circuit. This oscillating circuit are used as tuned circuits. This inductor are used for low pass filter and to suppress this conductive electromagnetic noise. The relays also operate on the principle of inductance. The last one is the transformer, which works on the principle of mutual inductance. When a current flows through a conductor, a magnetic field is developed around it, and the amount of field developed depends upon the magnitude of current flowing through the conductor. If the amount of current is large, then the field developed will be large. The direction of the field around a conductor is given by Fleming's right hand rule, which states that if you hold the conductor through a right hand and your thumb points in the direction of a current, then the finger will encircle in the direction of magnetic field, which is given by B. Now let us look at Faraday's law of electromagnetic induction, which states that if the changing magnetic field links with the coil, there will be an EMF induced in it. The induced EMF is equal to the rate of change of flux linkage. Now let us elaborate it. See, we have seen that when a current flows through a coil, a magnetic field is developed around it. This is the current and this is the magnetic field. Now, if the current is varying in nature, means it is suppose sinusoidal in nature, then the flux developed around this conductor will also be varying nature. If this varying flux will link the conductor, there will be an EMF induced in it. This is the principle of induction. Now let us see what Lenz law states. The induced EMF opposes every cause which produces it. See what happens when this voltage is developed around the conductor due to the varying flux change, then this voltage will oppose, therefore a negative sign is incorporated in it, that this voltage will oppose this change of flux linkage. This is the combination of Faraday's law of electromagnetic induction and the Lenz law. Now let us look at how the fields are distributed around a solenoid. If a current, as indicated, flows through the solenoid, then the field is developed as shown by the red lines. As we know that the flux developed around the conductor is proportional to the amount of current flowing through the conductor. Therefore, we can rewrite this equation as phi equals to Li, where L is the constant of proportionality, is called the inductance of the solenoid or conductor. If there are n number of turns in the solenoid, then this equation can be rewritten as L equals to n phi by I. This is the equation of inductance in a conductor or solenoid. From the Faraday's law of electromagnetic induction, we know that E equals to minus d phi by dt. Therefore, we can rewrite this equation as E equals to minus d by dt of phi, and phi is equals to Li. Therefore, this equation will be rewritten as E equals to minus L di by dt. This is another equation of voltage developed around an inductor when we know the inductance and the rate of change of current. We have seen that how magnetic field is distributed around the solenoid. Now, when we insert iron core inside the solenoid, the number of magnetic field line will increase, as reluctance offered by the iron core is less because of its high permeability. Now let us calculate the inductance of this solenoid. Let us suppose L is the length of the solenoid, A is the cross-sectional area of the core inside the solenoid, N is the number of turns, and mu is the permeability of the core. So let us calculate the inductance of the solenoid. But before that, let us review some basic equations of magnetism. The first one is phi equals to BA, where phi is the magnetic flux, B is the magnetic flux density, and A is the cross-sectional area of the core. The next one is B equals to mu H, where B is the magnetic flux density and H is the magnetic field strength, where mu is the permeability of the material. It is given by mu equals to mu naught mu r, where mu naught is the permeability of the air and mu r is the relative permeability of the material. Now this last one equation is the H equals to Ni by L, where H is the magnetic field strength, N is the number of turns in the solenoid, I is the current flowing through the conductor, and L is the length of the solenoid. This is equation number 3. Now, as we have seen previously, that inductance is given by L equals to N phi by I. Putting the value of phi from equation 1, we can write L equals to N BA by I, which can be rewritten as L equals to N B equals to mu H A by I. It is again rewritten as L equals to N mu H equals to N by L from the equation number 3, N I by L into A upon I. This I will cancel, then the inductance of the solenoid in terms of its parameter is given by L equals to mu N square A by L. This is the inductance of the solenoid. In terms of its area of the core, L length of the solenoid, number of turns, and mu is the permeability of the material. We know that phi is equals to Li, where L is the inductance of the inductor and I is the current through the inductor. From the Faradays Law of electromagnetic induction and the Lenz law, we can write E equals to minus d by dt, which is equals to minus L di by dt. Therefore, voltage across the inductor is given by V equals to minus L di by dt, where L is the inductance of the inductor and di by dt is the rate of change of current through the inductor. It is an important equation of inductor as it tells very useful information about the inductor. Now let us suppose there is an instantaneous change in current through the inductor. As you can see that the slope of this instantaneous change is infinite, it will require an infinite amount of voltage for such a change to occur, which is physically or practically not possible. Therefore, inductor opposes sudden change in current through it. And this is the reason why current lacks the voltage in case of inductor. Now let us calculate the instantaneous power dumped inside the inductor, which is equals to Vi. Putting the value of V from this equation 1, we can write P equals to L di by dt into I. For calculating the energy stored inside the inductor, let us integrate this equation from minus infinity to t p dt. Now assuming, first solving it and then assuming that the initial current through the inductor is 0, we can calculate the energy stored inside the inductor is equals to 1 by 2 Li square. Now let us look at the voltage and current waveform of the inductor. For that, suppose a voltage Vs is applied across the inductor through a switch S1. At time t0, let this switch is closed. Therefore, a voltage of magnitude V is applied across the inductor. As we know that the inductor opposes sudden change of current through it, therefore the current through the inductor builds up slowly. During this time, a voltage of negative polarity to the applied DC voltage is developed across the inductor. During the steady state of the current, that is as shown in the diagram, there will be no voltage developed across the inductor because there is no rate of change of current. Now at time t1, when the voltage across the inductor is equals to 0, there should not be any current. But as we know that the current through the inductor does not change instantaneously, therefore current decreases slowly. And during this time, a voltage is developed across the inductor which supports this current. This is like this. If you have any query or suggestion, please comment in the comment box. Don't forget to like and share this video and subscribe this channel.